Hi, this is Pat Kelly. Okay, in this problem, I've got things spaced out for us here, but this is what they give us. They actually give us everything in purple here, but we focus first on this f vector function, and the directions tell us to show that that f is conservative, and then once we've done that, we're supposed to verify that this integral, should look familiar to you, our work calculation, yields the same results for either of these two parametric representations of the same path. Okay, let's just start where they ask us to start, is to show that this function is conservative. What I would do is, even in the space I think I have right here, you're checking if the partial of m with respect to y, does that equal the partial of n with respect to x, and that's actually a question mark at first, even though we know the answer because they told us to show it's conservative. So that should be true. Let's do it. The partial of m is right here. The x squared is m, and the partial of that with respect to y is 0. And we're going to ask if that equals, let me even set us up with our question mark first. I don't want to give away the answer. I think I already did. The n is y, and the partial of n with respect to x, right? Partial of y with respect to x is also 0. I tried to make that as suspenseful as I could, but 0 equals 0, that's a check mark. But they told us it was going to be conservative. We just had to verify that. All right, now the real beef of this problem is that we want to calculate this integral for each of these two different r functions. And they mention in the directions that they are parametric representations of the path, and you can see that they're parametric representations of the path with those parameters. And the significance of that then is that I'd like to start off by rewriting this integral, a different version of it, the one that's most useful to us when we have parametric representations. You've seen this before. This integral equals the integral from a to b of that f vector if we express it as a function of the t, the parameter, dotted with the r prime vector of t and then dt. Okay, that should look familiar to you. And I wanted to get it up front for us because now I'm going to follow this formula, if you will, to solve each of these two integrals. So you can see we do need that r prime. That's why this problem is in a calculus book, right? As we're going to do a derivative. So I would start my work off for either of these two by doing a derivative, right? So let me do the work for this one, get an answer. Then we'll slide over there and do comparable work for that one. We should get the same answer, right? So r1 prime of t. This is the easy stuff now, right? Derivatives, I've been doing them forever, plus 2tj vector. Okay, no problem. I'm also still looking at my formula. See what else you need is that f vector in terms of t. So I'll slide over here, and I'm doing this right below, really only so that I can get them lined up for my next step, which is going to be to do that dot product. So f of t, that's when we look to the f function, and you're putting in for x and y, you're putting in for x and y these components, right, from your r equation. This is x, so t squared, I vector, plus from our f function, the y, I'm putting in this t squared component, and that's times j vector. And then we're ready for the integral. So that integral of f dotted with dr, that's what they asked us to find in the directions. But right away on the other side of the equal sign, let's use the other version, I guess my pink version. We're looking for the integral from 0 to 1 for our limits of integration. Let's do that dot product right now. Is the dot product between f and r prime. So I'm just multiplying t squared times 1, adding and multiplying t squared times 2t, so 2t cubed, and that's all dt. And see how it comes down to a nice integral, well behaved. Let's actually do this integral. T squared is going to go up to the 3 power divided by 3, plus t cubed goes up to t to the 4th, but divide by 4, so t to the 4th, divide by 4, but there's a 2 here, so I'll end up dividing by 2. And we're doing all of this from 0 to 1. So I'm getting a 1/3 plus 1/2. Subtract 0, so there's zeros everywhere, that's good. We can get a final answer, common denominator of 6, so this is going to be 2 plus 3 is 5/6. All right, final answer for the first part. I'll switch colors if you want. Second part, different looking R functions, still parametrically represented, so I can still use this formula. Of course, be flexible with me here. I'm going to need a theta everywhere that there's a t, no big deal. But the important part in this problem is that we should end up getting that same value of 5/6 because f is conservative, as we showed at the beginning of the problem. Okay, so let's get to it. My r prime vector of theta will equal, and now I'm doing my derivatives here. This is just cosine of theta times the I vector plus 2 times sine theta, and then times cosine theta. Let's see, 2 in front, sine drop down to the 1 power, multiplied by the derivative of sine is cosine. Just making sure I get that right. And then the j vector. Okay. And then similar to what I did before is right underneath that, I'd really like to take a look at the f vector in terms of the parameter, just so I can do my dot product in the next step. So now I'm looking back at that f function, but I'm using for x and y these parts here. Right? The sine of theta is my x, the sine squared is my y. So the first thing I need is x squared. That's going to be a sine squared theta times the I vector plus, the plus coming from my f, y, so that's just this part, sine squared of theta times j. And then we get into our integral. I think I might need some space, so I'll just slip over here. The integral of that f dotted with dr equals, and I'm still using that formula in pink, but theta for t. So the integral, theta goes from 0 to pi over 2. All right, let's do the dot product, where I'm looking at the dot product of these two guys, sine squared times cosine. So I'm going to have a cosine of theta times the sine squared of theta. I have to add multiplication of these two components. Looks like there's a 2 sine cubed of theta times cosine of theta, and all of that is times a d theta. All right. Oh my gosh, okay, big integral with trig expressions. Don't worry, this actually behaves pretty well. I'd be thinking of u substitution from ages ago, and I think I'd let my u equal sine of theta, because then of course du equals cosine of theta d theta. The reason why that's so cool is because this cosine and this cosine, you can imagine factoring out of the parentheses, pair it with the d theta, it's all going to dissolve into the du. And so what you're looking at is the integral of u squared plus 2, right? U cubed du. And I do want to change my limits of integration. They were thetas, now let's change them to u's. Plug in here. Sine of 0 is 0. Sine of pi over 2 is 1. Take a look at what you have. Let's pan out here and compare. Integral from 0 to 1, u squared plus 2u cubed. Here was the integral 0 to 1 of t squared plus 2t cubed. Yeah, this is equal to 5, 6. All right, that's what they wanted us to show. No surprise, they should be the same. Okay, go practice them on your own, and you'll get it.